What if I told you that some of the oldest objects in the entire universe might still be out there hidden in plain sight? Picture this, the very first stars, blazing to life in the darkness of the cosmos over 13 billion years ago, could still be burning today. It's a thought that stretches the imagination, but astronomers are seriously asking this question. These ancient celestial giants, known as Population 3 stars, were the pioneers of light in a young, chaotic universe. They were massive, short-lived, and forged the very elements that would eventually make planets and us possible. But here's the mind-blowing part. Some of them might not have died out. They might still be shining, faint and distant, waiting to be found. Think about how incredible that is. These stars would be relics from a time when the universe was nothing like it is today. No galaxies as we know them, no planets, just vast clouds of raw hydrogen and helium collapsing under gravity's pull. The conditions back then were so extreme that these stars could have been hundreds of times more massive than our Sun, burning fiercely before vanishing in spectacular supernovas. But what if not all of them met that fate? What if some survived, drifting through the cosmos like living fossils from the dawn of time? The idea challenges everything we thought we knew about stellar lifespans and the evolution of the universe. This isn't just science fiction, it's a real mystery that astronomers are racing to solve. Cutting-edge telescopes and simulations are peeling back the layers of cosmic history, searching for clues that could reveal whether these ancient giants are still out there. And if they are, what would that mean for our understanding of the universe's earliest moments? Could they hold secrets about how the first galaxies formed, or even how life itself became possible? We're about to dive into the latest theories, the mind-bending possibilities, and the high-stakes hunt for these elusive stars. So buckle up, we're going on a journey across space and time, to the very edge of what we know and beyond. To grasp how extraordinary these first stars were, we have to rewind to a universe utterly alien to our own. Picture a cosmos still in its infancy, no galaxies, no planets, not even the faintest glow of starlight. Just an endless sea of hydrogen and helium gas swirling in the darkness for millions of years. Then something miraculous happened. Gravity began pulling these primordial clouds together, squeezing them tighter and tighter until ignition. The first stars burst into existence like beacons in the void, and the universe would never be the same again. These weren't just any stars, they were titans, hundreds of times more massive than our Sun, burning at temperatures so extreme they could fuse elements in seconds that would take modern stars millions of years. And here's the twist, they were made of nothing but hydrogen and helium. No carbon, no oxygen, none of the heavier elements that fill today's cosmos. That purity made them unimaginably bright and short-lived, exploding in violent supernovas after just a few million years. But in their brief lives, they did something revolutionary. They cooked the first heavy elements in their cores, scattering them across space when they died. Those ashes became the building blocks for everything that followed. Galaxies, planets, and eventually us. Now, here's where the mystery deepens. If these stars were so massive and short-lived, how could any still exist today? The answer might lie in the quieter outliers, the smaller population, 3 stars that could have formed in rare, less dense pockets of the early universe. While most of their colossal siblings flared and died quickly, these smaller ones might have burned slower, fainter, lasting billions of years longer than we ever thought possible. Finding one would be like discovering a living dinosaur, a direct window into the universe's darkest, most formative age. Astronomers are scouring the farthest edges of observable space, where light takes so long to reach us that we're essentially peering back in time. New telescopes like the James Webb Space Telescope are designed to detect the faintest glimmers from these ancient objects, and if they succeed, it would rewrite our understanding of stellar evolution, proving that some of the universe's first lights never flickered out. They've been shining all this time, quietly witnessing the rise of everything we know. What made these ancient stars so radically different from anything we see today? The answer lies in their ingredients. Population 3 stars were born from a cosmic recipe we'll never see again: pure hydrogen and helium, uncontaminated by even a speck of heavier elements. Imagine a universe where no star had ever died, where no supernova had ever scattered metals through space. That's the environment where these giants took shape, and it forced them to play by entirely different rules. Without carbon, oxygen, or other elements to help cool collapsing gas clouds, these stars had to form under extreme conditions, growing to staggering sizes that dwarf anything in our modern night sky. Their sheer scale defies belief. While today's stars might reach a few dozen solar masses at most, population 3 stars could have tipped the scales at several hundred times the mass of our Sun. That kind of bulk came with consequences. Their cores burned at temperatures so ferocious they could fuse hydrogen into helium in a fraction of the time it takes modern stars. Some may have lived fast and died young, lasting only a couple million years before exploding in supernovas so powerful they would have outshone entire galaxies. But here's where the plot thickens. Not all of them may have followed that script. Recent simulations suggest a tantalizing possibility. While most of these primordial giants met violent ends, a handful might have formed in quieter corners of the early universe, places where gas clouds weren't as dense, allowing smaller, more stable stars to emerge. These outliers could have been just tens of times the mass of our Sun, burning slower and steadier, potentially surviving for billions of years longer than their colossal siblings. It's like finding a single candle still flickering in the ruins of an ancient civilization, a fragile but direct link to a lost era. The hunt for these survivors isn't just about ticking a box in astronomy textbooks. If they exist, they'd be cosmic time capsules, preserving pristine material from before the first heavy elements polluted the universe. Studying their light could reveal secrets about how the earliest structures formed, how the first black holes grew, even how the conditions for life were set in motion. Every photon reaching us from one of these stars would carry imprints of a universe we've only ever theorized about. A universe before chemistry, before planets, before complexity. And that's what makes this search so thrilling. We're not just looking for old stars, we're chasing ghosts from the universe's birth, hunting for the last witnesses to a time when everything was simpler, hotter, and more extreme. If we find one, it won't just rewrite a chapter in astrophysics, it'll give us a front row seat to the cosmic dawn itself. The lifespan of those first stars is one of the most fascinating puzzles in cosmology. When we say these cosmic titans lived fast and died young, we're talking about stellar lives measured in mere millions of years, a blink of an eye compared to stars like our Sun, which burns steadily for billions. Their enormous mass meant they burned through their nuclear fuel at breakneck speeds, shining with incredible brilliance before meeting cataclysmic ends. But here's where the story takes an unexpected turn. While most population 3 stars followed this dramatic script, there's growing evidence that not all of them played by the same rules. Imagine a vast, uneven landscape in the early universe, some regions dense with gas, others more sparse. In those quieter pockets, where matter wasn't as tightly packed, smaller population 3 stars might have formed. These wouldn't have been the behemoths hundreds of times the Sun's mass, but perhaps just 10 or 20 times heavier. That slight difference could have changed everything. Smaller stars burn slower, cooler, stretching their lifespans from millions to potentially billions of years. It's like comparing a roaring bonfire to a carefully tended candle. One consumes itself in a spectacular blaze, while the other glows softly for ages. Now, the big question, could any of these smaller first stars still be shining today? The idea isn't as far-fetched as it sounds. The universe is nearly 14 billion years old, but a star formed in those early epochs with just the right mass and conditions might still be holding on. The challenge is finding them. These ancient survivors would be incredibly faint by now, their light stretched and dimmed by cosmic expansion. They'd likely be hiding in the outer reaches of galaxies or drifting through intergalactic space, their origins disguised by time. This isn't just theoretical speculation. Advanced computer simulations show that while the vast majority of population 3 stars would have vanished eons ago, a tiny fraction, perhaps 1 in a million, could have had the right combination of mass and environment to endure. Spotting one would be like finding a needle in a galaxy-sized haystack, but the payoff would be enormous. These stars would be pristine time capsules, their composition untouched by the heavier elements that later generations of stars produced. Studying them could reveal secrets about the universe's chemical infancy, how the first black holes formed, even how the initial seeds of galaxy formation took hold. The hunt is already underway. Telescopes like the James Webb Space Telescope are peering deeper into space and further back in time than ever before, scanning for the faint, telltale signatures of these elusive objects. If they succeed, it would be one of the most profound discoveries in modern astronomy, rewriting our understanding of stellar evolution and the early cosmos. So while most of the first stars may be long gone, the possibility that a few still linger out there keeps astronomers searching the skies with renewed excitement. After all, in a universe this vast and ancient, the most extraordinary surprises often come from the quietest corners. Detecting these ancient stars is one of astronomy's greatest challenges, not just because they're rare, but because the universe itself has conspired to hide them. Imagine trying to spot a single candle flickering on the other side of an ocean, then stretching that candle's light until it's barely a whisper. That's what scientists are up against. Over billions of years, the expansion of the cosmos has stretched the light from these stars into the infrared spectrum, far beyond what human eyes or even standard telescopes can see. Their signatures are buried in a sea of cosmic noise, drowned out by younger, brighter stars and the glow of interstellar dust. Even if a population 3 star still burns today, its light would be staggeringly faint, redshifted so dramatically that it's practically invisible to most current instruments. It's like tuning an old radio, searching for a station that's barely transmitting except instead of static. You're sifting through the light of billions of younger stars, galaxies, and quasars. Traditional telescopes simply aren't sensitive enough to pick out these ancient relics from the cosmic background. But here's where technology is turning the tide. Next-generation observatories like the James Webb Space Telescope are game changers, designed to peer into the infrared spectrum with unprecedented clarity. Webb can detect light that's been stretched by the universe's expansion over eons. Its massive mirror and cutting-edge instruments act like a time machine, capturing photons that have traveled nearly the entire age of the cosmos. Even so, the hunt is painstaking. Astronomers must comb through vast swaths of sky, looking for telltale chemical fingerprints, signatures of pure hydrogen and helium, untouched by heavier elements. But the challenges don't end there. Even if we spot a candidate, confirming its identity is another hurdle. These stars wouldn't look like the familiar points of light in our night sky. Their atmospheres, devoid of metals, would behave differently, absorbing and emitting light in ways modern stars don't. researchers rely on sophisticated models to interpret these anomalies, comparing observations against simulations of how population 3 stars should appear. It's a cosmic detective story, piecing together clues from the faintest whispers of light. And then there's the question of where to look. The first stars likely formed in isolated pockets of the early universe, far from the crowded galactic neighborhoods we see today. Some might still drift in the voids between galaxies, while others could be hidden in the outer fringes of ancient star clusters. Each potential hiding place requires a different search strategy, adding layers of complexity to an already daunting task. Yet despite these obstacles, the pursuit is heating up. New algorithms and machine learning tools are helping astronomers sift through mountains of data, flagging unusual objects for closer study. Upcoming missions, like the European Extremely Large Telescope with its 39-meter mirror, promise even sharper views. The race is on to capture that first definitive glimpse of a star from the cosmic dawn, a discovery that would rewrite our understanding of stellar evolution and the universe's earliest chapters. So while the challenges are immense, so too is the potential reward. Finding one of these ancient stars wouldn't just be a triumph of technology. It would be like uncovering a lost page from the universe's diary, written in the faint glow of a survivor from the very first generation of light. Even if the first stars vanished billions of years ago, their legacy isn't lost, it's written into the chemistry of the cosmos. Think of it like cosmic archaeology. Just as paleontologists study fossils to understand long-extinct creatures, astronomers can examine the oldest surviving stars in our galaxy to uncover secrets about their long-dead ancestors. These ancient celestial relics, known as metal-poor stars, are the second generation of stars ever formed, and they carry chemical imprints of the very first supernova. It's as if they've preserved fragments of a vanished world in their atmospheres, waiting for us to decode them. These second-generation stars are rare, but they're out there, scattered across the Milky Way, often hiding in its dim outer reaches or within ancient globular clusters. What makes them so special is their composition. Unlike modern stars, which are polluted with heavier elements like iron and oxygen, these relics contain barely a trace of metals. That's because they formed from the ashes of population 3 supernova before the universe had been thoroughly seeded with heavier elements. When those first stars exploded, they spewed their fused material into space, and the next generation of stars formed from those enriched clouds. By studying the specific ratios of elements in these metal-poor stars, scientists can reverse engineer the properties of the long-gone giants that came before them. Here's where it gets even more fascinating. Not all population 3 stars died the same way. Some likely exploded as pair instability supernova cataclysmic blasts so powerful they left no remnant behind, just a burst of pure energy and newly forged elements. Others might have collapsed directly into black holes, swallowing much of their material and leaving fewer traces behind. The chemical fingerprints in second-generation stars can tell us which scenario played out. For example, an unusually high ratio of carbon to iron in an ancient star might hint at a pair instability explosion, while a lack of certain heavy elements could point to a direct collapse. It's like finding different types of ash in a fire pit and deducing whether the fire burned hot and fast or smoldered slowly. The hunt for these cosmic time capsules has already yielded some tantalizing clues. Stars like He0 107-5240, one of the most metal-poor stars ever discovered, have compositions that suggest they formed from the debris of just 1 or 2 population 3 supernova. Others, like SMSS J0313-6708, contain surprising amounts of lighter elements like carbon but almost no iron. a possible signature of those elusive pair instability explosions. Each of these stars is like a single page from a lost library, offering glimpses into the lives and deaths of the universe's first luminous giants. But the detective work doesn't stop there. Advanced telescopes and spectrographs are now analyzing these ancient stars with unprecedented precision, measuring the faintest traces of elements in their light. Projects like the Sloan Digital Sky Survey and the upcoming European Extremely Large Telescope are expanding the search, scouring the skies for even rarer, more pristine examples. The goal: to find a star so metal-poor it might as well be a direct descendant of the very first generation, a star that could unlock the final secrets of how the cosmos transformed from a dark, empty void into a universe brimming with light and complexity. So while we may never spot an original population, 3 stars still burning, their echoes are all around us, etched into the stars we can see today. Every time astronomers analyze the light from one of these ancient relics, they're piecing together a cosmic origin story, one supernova remnant at a time. Dark matter, the invisible glue holding galaxies together, might hold the key to one of cosmology's most puzzling questions. How could any of the first stars still be shining today? Picture this: in the early universe, vast clouds of dark matter formed halos around collapsing gas, acting like cosmic scaffolding that guided the birth of those primordial stars. But here's the twist: some theories suggest these halos didn't just shape the stars, they might have protected them. Imagine dark matter as a shield, absorbing energy or altering the way these stars burned, slowing their inevitable demise. It's a radical idea, but if true, it would mean the universe's most elusive substance played an active role in preserving its oldest luminaries. The math behind this is mind-bending. Normal stars like our Sun fuse hydrogen in their cores, but a population 3 star wrapped in a dense dark matter halo could have behaved differently. Some models propose that dark matter particles colliding in the star's core might have released energy, supplementing nuclear fusion and reducing the star's reliance on its hydrogen fuel. Think of it like a car running on 2 fuel sources, gasoline and electricity, extending its range far beyond what either could achieve alone. In stellar terms, this could have stretched a million-year lifespan into billions, allowing a handful of these ancient objects to persist undetected in the modern cosmos. But how would we even begin to look for such stars? Their dark matter influence would leave subtle fingerprints. Unlike normal stars, which dim predictably as they age, these shielded relics might glow with unusual stability, their light tinged with telltale signatures of dark matter interactions. Telescopes hunting for them wouldn't just scan for faint points of light, they'd search for anomalies in energy output or chemical composition that defy conventional astrophysics. It's like tracking a ghost by the way it bends the air around it. Critics argue the idea stretches plausibility. Dark matter, by definition, rarely interacts with normal matter, so how could it sustain a star? Yet proponents counter that the extreme densities in early cosmic environments might have allowed fleeting interactions we'd never see today. It's a debate that hinges on unknowns, and that's what makes it thrilling. If evidence emerged to support this theory, it wouldn't just rewrite the story of the first stars, it would redefine our understanding of dark matter itself. The implications ripple outward. If dark matter halos preserved even a fraction of population 3 stars, their modern counterparts could be hiding in plain sight, masquerading as faint, ordinary stars while harboring secrets from the dawn of time. Discovering one would do more than solve an astronomical mystery. It would unveil a hidden dialogue between the visible and invisible universe, a conversation that's been ongoing since the first flickers of light pierced the cosmic dark. Simulating the early universe isn't just about running equations. It's like reconstructing a cosmic crime scene where the evidence has faded over billions of years. Supercomputers today act as time machines, crunching mind-boggling calculations to recreate that primordial darkness before the first stars flickered to life. These models start with the universe's raw ingredients, vast clouds of hydrogen and helium, peppered with the subtle gravitational ripples left over from the Big Bang. Then physics takes over, gas clumps collapse, temperatures soar, and suddenly, virtual stars ignite in the digital void, mirroring what astronomers believe happened 13 billion years ago. What's astonishing is how detailed these simulations have become. They don't just show stars forming, they reveal the chaotic environments where these giants were born. Turbulent gas streams, shock waves from collapsing matter, even the magnetic fields that might have shaped stellar nurseries. It's a level of precision that lets scientists tweak variables like cosmic chefs adjusting a recipe. What if dark matter was denser here? What if the gas cooled slightly faster there? Each run unveils new possibilities, and one pattern keeps emerging. While most of these first stars lived fast and died young, a tiny fraction might have formed in quieter pockets where conditions allowed slower, more stable burns. The simulations paint a compelling picture. Imagine the early universe as a vast, uneven landscape. In some regions, gas piled up so densely that stars hundreds of times the sun's mass flared like fireworks, vanishing in mere millions of years. But in other, more isolated patches, matter was spread thinner. There, smaller population 3 stars could have formed, still massive by today's standards, but not the ultra-bright behemoths. These outliers might have burned steadily for billions of years, fading but never quite flickering out. Here's where the hunt gets strategic. These models don't just say, "Look anywhere," they predict where survivors are most likely to hide. The answer, the cosmic boondocks, far from the crowded galactic centers, in the sparse outskirts of ancient galaxies or drifting through intergalactic voids, these relic stars could still glow faintly. Telescopes like JWST are targeting these exact regions, guided by simulations that act as treasure maps to the universe's oldest light. Yet even with cutting-edge tech, finding them is a needle in a haystack challenge. The simulations suggest these stars would be incredibly rare, perhaps 1 in a billion. Their light, stretched by cosmic expansion, would be achingly dim, blending into the infrared haze of the cosmos. But the payoff would be revolutionary. Spotting even one would validate decades of theoretical work, proving that the universe's first generation of stars didn't entirely vanish. They'd be more than astronomical curiosities, they'd be time capsules, holding pristine secrets about how everything began. The most thrilling part, these models keep evolving. Every breakthrough in computing power or physics refines the simulations, sharpening our cosmic vision. Maybe the next run will reveal a new hiding place, a subtle signature to watch for. Or perhaps it will uncover an entirely unexpected way these ancient stars could have endured. One thing's certain, as long as the simulations keep pointing to possibilities, astronomers will keep searching the skies, hoping to catch the faintest whisper of light from the dawn of time. Among the most intriguing possibilities in the hunt for the universe's first stars is this. What if some didn't explode at all? Instead of ending in supernovas, these ancient giants might have collapsed silently into black holes, vanishing without the fireworks we'd expect. These wouldn't be the black holes we know today, formed from dying stars or galactic mergers. These would be primordial black holes, relics from the cosmic dawn, and if they exist, they could be hiding in plain sight, warping the fabric of space around them in ways we're only starting to detect. Think about the sheer scale of these hypothetical objects. Population 3 stars were so massive that if they collapsed directly into black holes, those remnants could range from a few times the mass of our Sun to hundreds or even thousands of times heavier. Unlike modern black holes, which form from stars enriched with heavier elements, these primordial ones would carry the pristine signature of the early universe, pure hydrogen and helium, untouched by the chemical complexity that came later. And here's the kicker, they might not be alone. Some theories suggest these black holes could cluster in the darkest corners of galaxies or drift unseen between them, their gravity subtly tugging on everything around them. The challenge is finding something that emits no light. Astronomers have to rely on indirect clues, tiny distortions in starlight, unexplained movements of nearby stars, or even ripples in spacetime itself. One tantalizing hint comes from gravitational wave detectors like LIGO, which have picked up signals from black hole mergers that don't quite fit the expected profile. Could some of these events involve primordial black holes from the first generation of stars? It's a provocative idea and it's gaining traction, but the implications go beyond just spotting these cosmic ghosts. If primordial black holes exist, they could solve multiple mysteries at once. For decades, scientists have debated the nature of dark matter, the invisible stuff making up most of the universe's mass. Could some of it actually be these ancient black holes lurking undetected since the beginning of time? It's a long shot, but not impossible. Simulations show that even a small population of primordial black holes could account for missing mass in galaxies, their gravity shaping cosmic structures in ways that match our observations. The search is heating up. New telescopes and advanced algorithms are scanning the skies for anomalous stars that wobble without visible cause, microlensing events where distant light bends inexplicably, or even strange heat signatures with no apparent source. Each potential clue brings us closer to answering whether these elusive remnants of the first stars still walk among us, invisible architects of the cosmos. And if we find them, it would rewrite not just the story of stellar evolution, but our entire understanding of how the universe grew from darkness into light. The next generation of telescopes isn't just upgrading our view of the cosmos, it's handing us a time machine. With instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope, we're not just peering deeper into space, we're staring further back in time than ever before. These aren't incremental improvements, they're leaps into uncharted territory, designed to catch the faintest whispers of light from an era when the universe was in its infancy. And if there's even a single population 3 star still burning out there, these technological marvels might finally bring it into focus. Take the James Webb Space Telescope, for example. Its massive gold-coated mirror isn't just bigger than Hubble's, it's optimized for infrared light, the very wavelength stretched and dimmed by billions of years of cosmic expansion. That means it can detect the telltale glow of ancient objects that would be invisible to older telescopes. But Webb is just the beginning. The Extremely Large Telescope, currently under construction in Chile, will boast a mirror nearly 39 meters across, large enough to collect light so faint it's like spotting a firefly on the moon. Together, these instruments form a dream team for hunting the universe's oldest stars, each complementing the other's strengths. What makes this search so revolutionary isn't just the technology, it's the strategy. Astronomers aren't randomly scanning the skies, they're targeting specific regions where simulations suggest these relics might hide. The outer edges of distant galaxies, the sparse voids between cosmic structures, even the halos of dark matter surrounding ancient star clusters, all are prime hunting grounds. And they're not just looking for any faint dot of light. They're searching for chemical fingerprints, stars with almost no heavy elements, whose light carries the unmistakable signature of hydrogen and helium untouched by later generations of supernova. But here's the catch. Even with these advanced tools, spotting a population 3 star would be like finding a single grain of sand on a beach the size of a planet. The light from these objects, if they exist, has traveled for billions of years, stretched and diluted by the expanding universe. To separate that signal from the cosmic background noise, scientists are deploying cutting-edge techniques like spectral analysis, which breaks starlight into its component colors to reveal hidden details about its composition. They're also using machine learning to sift through mountains of data, training algorithms to flag the subtlest anomalies that might indicate an ancient survivor. The stakes couldn't be higher. If one of these telescopes captures definitive proof of a first-generation star still shining, it wouldn't just be a headline, it would rewrite textbooks. Such a discovery would challenge our understanding of stellar lifespans, force us to rethink how the earliest structures in the universe formed, and maybe even offer clues about the nature of dark matter. It's the kind of breakthrough that doesn't just answer old questions, it sparks entirely new ones. And the best part, we're on the brink of this revolution right now. Every new observation, every dataset analyzed, brings us closer to potentially spotting a cosmic relic thought lost to time. Whether it's Webb's infrared eyes piercing the veil of the distant universe or the extremely large telescope's unprecedented resolution, one thing's certain: the tools we need to solve this ancient mystery are finally here. The universe's oldest light may yet have a story to tell, and we're just starting to listen. Even if every one of those first stars vanished billions of years ago, their fingerprints might still linger in the faint glow of the cosmos itself. Think of it like standing in a dark room long after a flashbulb has gone off. You might not see the bulb anymore, but its afterimage lingers, imprinted on your vision. The universe works in a similar way. The cosmic microwave background, that ancient light left over from the Big Bang, could hold subtle distortions caused by the very first stars flaring to life and dying in the darkness. These distortions aren't just random noise, they're cosmic hieroglyphics waiting to be decoded. The key lies in how those early giants shaped their surroundings. When population 3 stars ignited, their ultraviolet radiation blasted into the surrounding hydrogen gas, stripping electrons from atoms in a process called reionization. This monumental shift didn't just light up the cosmos, it altered the very fabric of spacetime, leaving wrinkles in the cosmic microwave background that satellites like Planck have been mapping for decades. The patterns in that primordial light aren't uniform. They contain bumps and dips that tell a story about when and how those first stars switched on. It's like listening to an echo in a canyon and deducing the shape of the cliffs that produced it. But the echoes don't stop there. Some theories suggest that the explosions of those early stars might have left another kind of mark: gravitational waves. These ripples in spacetime, predicted by Einstein and now detectable with observatories like LIGO, could carry signatures of pair instability supernova, the universe's first catastrophic blasts. If we could trace those waves back to their source, we might uncover the final moments of stars that died before Earth even existed. Then there's the matter of chemical echoes. The heavy elements forged in those first stellar furnaces didn't just vanish, they seeded the next generation of stars, leaving behind a trail we can still follow today. Astronomers have found stars so metal-poor they're practically fossils, their atmospheres preserving the elemental ratios of those early supernovae like time capsules. By studying their light, we're essentially reading the recipes of the universe's first cook's recipes, written in the language of carbon, oxygen, and iron. And here's where it gets even stranger. Some of that ancient starlight might still be traveling through space, stretched into invisibility by cosmic expansion, but theoretically detectable as a faint infrared hum. Missions like NASA's upcoming SPHEREX telescope are designed to scan for this diffuse glow, a potential sea of photons from stars long gone. It's the ultimate cosmic detective story, searching for shadows of objects that may have disappeared before our galaxy even formed. The beauty of this hunt is that it doesn't rely on finding a single surviving star. Even if every population 3 star burned out eons ago, their collective impact on the universe was so profound that we might still piece together their story from the clues they left behind. Whether it's a ripple in space-time, a whisper in the cosmic microwave background, or a trace element in an ancient star, these signatures are more than just data. They're messages from the dawn of light itself. What if the oldest stars in the universe aren't just relics trapped in the distant past, but hiding right under our noses? The idea sounds like science fiction, but some astronomers are seriously considering it. Population 3 stars might be lurking much closer than we ever imagined, disguised among the familiar stars of our own galactic neighborhood. Think of it like finding a centuries-old painting hanging unnoticed in a modern art gallery, its true age obscured by time and wear. These primordial giants could be blending in with younger stars, their extraordinary origins hidden behind subtle but detectable clues. The key to uncovering them lies in their chemistry. Unlike modern stars, which contain traces of heavier elements like iron and oxygen, population 3 stars would be made of nothing but hydrogen and helium, pristine remnants of the early universe. Spotting one would be like finding a glass of pure water in a sea of soda. Their composition would stand out starkly against the metal-rich stars surrounding them. The challenge is that these ancient survivors, if they exist, would have aged over billions of years, their outer layers potentially polluted by interstellar dust or cosmic debris. But deep inside, their cores might still hold that original, untainted signature if we can peer deeply enough. So where would we even begin to search? The outer edges of our Milky Way are a prime hunting ground, far from the crowded galactic center, where star formation has been slower and less chaotic. These ancient relics could have drifted undisturbed. Some might even be passing through the halo of our galaxy, lonely wanderers from a time before the Milky Way took shape. Telescopes equipped with high-resolution spectrographs are already scanning these regions, analyzing starlight for the telltale absence of heavy elements. It's meticulous work, like sifting through a mountain of sand to find a single grain of gold, but the payoff would be astronomical. The implications of such a discovery would be staggering. A nearby population 3 star wouldn't just be a scientific curiosity, it would be a living portal to the cosmic dawn. Studying its light could reveal secrets about the conditions of the early universe with unmatched precision, offering clues about how the first black holes formed, how galaxies began assembling, even how the building blocks of life first scattered into space. And unlike distant, fading glimmers from the edge of observable space, a closer relic would give us crisp, detailed data, like examining a fossil under a microscope instead of through fogged glass. Yet skeptics raise valid questions. If these stars exist so close, why haven't we found them already? The answer might lie in their camouflage. Over eons, even a pure hydrogen-helium star could accumulate traces of heavier elements from interstellar space, masking its true nature. Or perhaps they're simply outshone by younger, brighter neighbors, overlooked in the glare of the modern cosmos. But with advanced tools like the James Webb Space Telescope and next-generation ground observatories, astronomers are refining their search, peeling back the layers of cosmic history with unprecedented precision. The hunt is far from over. Every time a metal-poor star is discovered, it reignites the possibility that a true first-generation survivor might be among them, waiting for its identity to be revealed. Whether these ancient giants are truly hiding in our backyard or not, the search itself is reshaping our understanding of stellar evolution and reminding us that the universe always has more surprises in store. Among the most mind-bending theories in modern astrophysics is the concept of dark stars, objects so strange they defy everything we know about stellar physics. Picture a star that doesn't shine from nuclear fusion but glows faintly from the annihilation of dark matter particles in its core. These hypothetical giants could rewrite the rules of cosmic history, offering a radical explanation for how some of the first stars might still exist today. Unlike the blazing furnaces of conventional stars, dark stars would operate on an entirely different energy source, burning slowly and steadily for billions of years longer than their fusion-powered counterparts. The theory hinges on dark matter's elusive properties. In the early universe, dense clumps of dark matter may have gathered in stellar cores, their particles colliding and releasing energy as they annihilated one another. This process could have sustained a star's heat and light without the need for nuclear reactions, creating objects that looked like stars but behaved unlike anything in our current catalogues. Imagine a celestial object glowing not from the fiery fusion of hydrogen but from the invisible crackle of dark matter, a cosmic engine running on fuel we can't even see. What makes dark stars so tantalizing is their potential longevity. While normal population 3 stars lived fast and died young, dark stars could have persisted for eons, their dark matter fuel depleting at a glacial pace. Simulations suggest some might still be out there, lurking in the distant cosmos, their faint infrared glow masked by the brilliance of younger stars. They'd be cold by stellar standards, perhaps just a few thousand degrees warm enough to emit heat, but nowhere near as luminous as the sun. Detecting these shadows of the cosmic dawn would require rethinking how we observe the universe. Traditional telescopes hunting for bright, hot stars would miss them entirely. Instead, astronomers would need to search for oddities, objects with the size and structure of stars, but emitting light that doesn't match any known fusion profile. The James Webb Space Telescope, with its unparalleled sensitivity to infrared wavelengths, might be the first instrument to spot one, picking up the telltale heat signature of a dark star hiding in plain sight. Yet the idea isn't without controversy. Critics argue that dark matter's weak interactions make it an unlikely power source for stars, and no definitive evidence of dark stars exists yet. But if they're out there, their discovery wouldn't just solve the mystery of surviving population 3 stars. It would confirm dark matter's role in shaping the universe's earliest structures. These cosmic anomalies would be more than astronomical curiosities. They'd be living proof that the universe's infancy was far stranger than we ever imagined. The hunt for dark stars straddles the line between established physics and bold speculation. Whether they exist or not, the mere possibility pushes us to question our assumptions about stellar evolution, dark matter, and the boundaries of cosmic possibility. And that's what makes this search so thrilling. It's not just about finding an odd star. It's about uncovering a hidden chapter in the story of how light first conquered the darkness. Imagine a star cast out from its home, drifting alone in the endless black between galaxies, no neighbors, no planets, just silence and emptiness stretching for millions of light years. This isn't science fiction. It's a real possibility for some of the universe's first stars. In the chaotic early cosmos, gravitational tugs from newborn black holes or collisions between protogalaxies could have flung these ancient giants into the void, sending them on journeys with no return. Today, they might still be out there, intergalactic wanderers untouched by time, their light so faint it's practically invisible against the vast darkness. These exiled stars would be cosmic ghosts, but finding them isn't impossible. Simulations suggest they'd likely follow predictable paths, ejected along trajectories that trace back to the universe's most violent early moments. The trick is knowing where to look. Unlike stars nestled in galaxies, these loners wouldn't have the backdrop of glowing gas or clusters to highlight them. Instead, astronomers would need to scan the deepest voids, searching for pinpricks of infrared light that don't belong. It's like searching for a single lit match in a desert at night, daunting, but not hopeless with the right tools. The James Webb Space Telescope could be the key. Its infrared capabilities are perfect for spotting these cold, ancient embers, and its sensitivity might just catch the faint glow of a star that's been drifting since the cosmos was young. Even a single detection would revolutionize our understanding of stellar evolution. These stars wouldn't just be relics, they'd be time capsules, preserving the pristine conditions of the early universe in a way that no galaxy-bound star could. Without the pollution of later supernova or interstellar dust, their composition would offer a crystal-clear snapshot of the cosmos before chemistry even existed. But the implications go deeper. If these exiled first stars are real, they could solve one of astronomy's biggest puzzles, the missing satellite problem. Galaxies like the Milky Way have far fewer small companion galaxies than simulations predict. Could some of those missing galaxies actually be lone population 3 stars, ejected so long ago that they're now invisible to current surveys? It's a radical idea, but it fits the math. Their absence would no longer be a flaw in our models, just a matter of perspective. The hunt is already pushing technology to its limits. New algorithms are being trained to distinguish these wanderers from background noise, while next-generation telescopes like the Nancy Grace Roman Space Telescope will scan wider swaths of sky than ever before. Every observation brings us closer to answering a profound question. Are we alone in the universe, not in the search for aliens, but in the cosmic sense? If stars can be exiled, drifting forever between galaxies, then the universe is even stranger and more wondrous than we imagined. And somewhere in that darkness, the first light might still be shining. The first stars may be long gone, but their fingerprints are everywhere, in the air you breathe, the ground beneath your feet, even the blood in your veins. When those ancient giants exploded, they didn't just vanish. They transformed the cosmos, scattering their elemental ashes across the void. Every atom of oxygen in your lungs, every fleck of iron in your blood, every speck of calcium in your bones was forged in the hearts of stars that died billions of years before Earth existed. Their legacy isn't just written in textbooks, it's woven into the fabric of our bodies and the world around us. Consider this: before those first supernova, the universe was a barren place. Only hydrogen and helium existed, simple elements too light to form planets, oceans, or life. But when population 3 stars reached the end of their short, fiery lives, they unleashed an alchemy unlike anything since. In their final moments, these titans fused lighter elements into heavier ones: carbon, nitrogen, oxygen, even gold and uranium, catapulting them into space in violent explosions. That stardust didn't just linger, it became the raw material for everything that followed. The second generation of stars formed from these enriched clouds, and with them came the first rocky planets, the first oceans, and eventually the first stirrings of life. The scale of this cosmic recycling is staggering. A single one of those early supernova could have spewed enough heavy elements to seed thousands of future solar systems. Over time, gravity pulled these scattered remnants together, mixing and remixing them into new stars, new worlds. Our own solar system is like a patchwork quilt stitched from the debris of countless stellar explosions, each contributing a piece of the puzzle. The iron in Earth's core, forged in a dying star's last gasp, the carbon in every living cell, a relic of nuclear fusion from a sun that shone before ours was born. Even the gold in your jewelry was likely born in the collision of two neutron stars, a cataclysm set in motion by the death of those first massive stars. But here's what's even more astonishing. We're not just made of stardust, we're made of rare stardust. The elements essential for life, like oxygen, carbon, and nitrogen, are cosmic rarities, making up less than 1% of the universe's ordinary matter. Without those first stars to create them, the cosmos might have remained forever barren, a sea of hydrogen and helium with no planets, no chemistry, no life. In a very real sense, we owe our existence to stars that lived fast, died young, and left behind the ingredients for everything that came after, and the story doesn't end there. Scientists are now using these elemental clues to trace the history of our cosmic ancestry. By studying the ratios of different isotopes in meteorites, the atmospheres of ancient stars, even the light from distant galaxies, they're piecing together how those first supernovas shaped the universe. Some elements, like europium or platinum, act as cosmic breadcrumbs, pointing back to the specific types of explosions that created them. Others, like lithium, hint at processes even older than the first stars, relics from the Big Bang itself. It's a detective story written in the periodic table, with each element offering a clue about where and when we came from. So while the first stars may have burned out long ago, their influence is anything but extinct. They set in motion a chain of events that led to galaxies, planets, and life itself. Every time you take a breath, you're inhaling atoms that once blazed in the hearts of those primordial giants. Every time you look up at the night sky, you're seeing the descendants of the stars that made our existence possible. Their light may be gone, but their legacy shines on in the stars above, the earth below, and even in the very cells that let you ponder their incredible story. Not every scientist is convinced the first stars looked or behaved how we imagine. Some researchers argue our models might be missing something fundamental. That population 3 stars could have taken forms so bizarre, we wouldn't recognize them even if we saw them. One radical theory suggests these ancient giants never ignited as traditional stars at all. Instead, they might have collapsed directly into black holes without ever shining brightly, like cosmic stillbirths vanishing into darkness before lighting up the universe. If true, it would mean the first sources of light weren't stars as we know them, but something far stranger, black holes glowing faintly as they devoured the gas around them. Then there's the quark star hypothesis. Under extreme conditions, the matter in these stars might have broken down into a soup of subatomic particles called quark-gluon plasma, creating objects denser than neutron stars but unlike anything in today's cosmos. Picture a stellar remnant so dense it defies the usual rules of physics, lingering for eons as a dark, exotic relic. These theoretical oddities could still exist, masquerading as black holes or dim neutron stars while hiding their true origins. Other scientists propose an even wilder idea. What if dark matter played such a dominant role in the early universe that it twisted star formation entirely? In this scenario, dark matter's gravity could have prevented gas clouds from collapsing into normal stars, instead forming dark stars powered by particle annihilation rather than nuclear fusion. These invisible giants might still be out there, radiating faint heat but no visible light, camouflaged against the cosmic background. The most provocative theories challenge whether population 3 stars were ever solitary to begin with. New simulations show that in the dense early universe, multiple massive stars might have formed in tight clusters, their gravitational dances leading to mergers or disruptions that altered their life cycles. Instead of dying in isolated supernova, they could have collided, forming intermediate mass black holes that then seeded the growth of supermassive black holes we see in galaxies today. It's a cosmic domino effect, one that would rewrite the story of how structure emerged in the universe. What keeps these alternative ideas alive is the sheer mystery of the early cosmos. Without direct observations, we're piecing together clues from an era that remains frustratingly out of reach. Every new telescope, every advanced simulation chips away at the uncertainty, but for now, the first stars remain as enigmatic as ever. Whether they burned bright and vanished or evolved into objects we've yet to discover, one thing's certain: the universe's opening act was far more complex than we ever imagined. Quasars, the brilliant beacons powered by supermassive black holes, aren't just cosmic spectacles, they're also time machines. Their light, traveling across billions of years, carries secrets about the universe's darkest corners, including clues that might lead us to the first stars. Here's how it works. When a quasar's light passes through ancient gas clouds on its way to Earth, those clouds absorb specific wavelengths, leaving behind chemical fingerprints in the quasar's spectrum. It's like shining a flashlight through fog. The patterns in the light reveal what the fog is made of. Some of these distant clouds date back to the era when the first stars were just beginning to illuminate the cosmos. By analyzing their absorption lines, the barcodes of elemental composition, astronomers can hunt for traces of material forged exclusively by population 3 stars. For instance, a complete absence of heavy elements like carbon or iron would suggest the gas was untouched by later generations of stars, preserving a pristine sample of the early universe. Even more tantalizing are the rare clouds showing slight enrichments of certain elements, which could be the scattered ashes of the very first supernova. These subtle chemical hints act like breadcrumbs pointing back to the stars that seeded them, but quasars offer more than just snapshots of ancient chemistry. Their light can also illuminate the structure of the early cosmos. Some quasar spectra reveal vast voids in the intergalactic medium regions where the gas appears unusually smooth. These might be the cosmic footprints of the first star's ionizing radiation, which stripped electrons from hydrogen atoms and permanently altered the fabric of space. Other spectra show strange clumps of dense gas, possibly the remnants of primordial star-forming regions where those early giants were born. Each quasar becomes a detective's notebook, filled with scribbled clues about how the first starlight sculpted the universe. The real breakthrough came when astronomers noticed something odd in the light from quasars at the edge of observable space. A handful of these distant objects show absorption lines with bizarre ratios of helium to hydrogen ratios that don't match anything produced by later stars or supernova. One explanation: these could be the echoes of pair instability supernova, the universe's first fireworks, triggered by the death of massive population 3 stars. If confirmed, it would be like finding the charred remains of a campfire lit at the dawn of time. Of course, interpreting these signals isn't straightforward. Quasar light doesn't come with a manual. It's a puzzle wrapped in noise and cosmic interference. Dust, intervening galaxies, and even the quasar's own turbulent environment can distort the signal. That's why astronomers cross-reference multiple quasars, looking for consistent patterns across different lines of sight. It's painstaking work, but the payoff could be revolutionary, a direct glimpse into the era when the first stars switched on and the universe woke from its dark age. And the hunt is accelerating. New instruments like the James Webb Space Telescope and next-generation spectrographs on ground-based observatories are analyzing quasar light with unprecedented precision. Every new dataset brings us closer to answering whether those primordial giants left behind detectable traces. or if their light vanished without a trace, leaving us to piece together their story from the faintest of cosmic whispers. The cosmic dark ages weren't just an absence of light, they were a profound silence, a universe so opaque that even if you'd been there, you wouldn't have seen your own hand in front of your face. Then something extraordinary happened. The first stars flickered on, and their ultraviolet radiation began tearing through the fog of neutral hydrogen that had shrouded the cosmos for millions of years. This was the epoch of reionization, a cosmic dawn where starlight punched holes in the darkness, transforming the universe from a dense, featureless void into the transparent expanse we know today. But here's the twist. That transformation wasn't just a one-time event. It was a delicate dance between creation and destruction, and the steps of that dance might hold the key to finding the first stars that started it all. Reionization didn't happen uniformly like a light bulb switching on. Instead, it unfolded in patches as bubbles of ionized gas expanded around clusters of the earliest stars and galaxies. Think of it like a frozen lake thawing in spring. Some areas melt first, while others linger in ice. By mapping these bubbles in the faint glow of the cosmic microwave background or the absorption lines of distant quasars, astronomers can estimate how many stars it took to reionize the universe. The math is staggering. Even if every star in those early epochs was a colossal, short-lived giant, you'd need billions of them to account for the ionization we observe. That raises a tantalizing question. If there were that many stars, could a few have slipped through the cracks, surviving longer than their peers in quieter corners of space? The timing of reionization offers another clue. Some models suggest the process started later than we'd expect if all population 3 stars died quickly. That delay hints at a possible mix of stellar lifetimes, perhaps a population of smaller, longer-lived stars contributing their ultraviolet photons over billions of years instead of millions. It's like realizing a campfire you thought burned out hours ago still has a few embers glowing beneath the ashes. These lingering stars wouldn't just be curiosities. They'd be cosmic Rosetta Stones, helping us decode how light first conquered the darkness. And then there's the role of black holes. Some theorists argue that early supermassive black holes feeding voraciously on gas and stars could have accelerated reionization with their intense radiation. But if that's true, it complicates the picture. Did stars do most of the work, or were black holes the unsung heroes? The answer could reshape our search for surviving first-generation stars. If black holes dominated, the stars might have been rarer than we thought, making any survivors even more precious. If stars led the charge, their sheer numbers increase the odds that a few still flicker in the shadows. What's remarkable is how much we've learned from what seems like nothing. The faint afterglow of the Big Bang, the ghostly absorption lines in quasar light, the subtle unevenness in the universe's transparency. These traces tell us not just about the first stars' lives, but about their deaths, their legacy, and possibly even their lingering presence. Every new observation peels back another layer, bringing us closer to answering whether the universe's first light still shines somewhere, a beacon from the dawn of time. Tiny, isolated dwarf galaxies could be hiding something extraordinary, the last surviving remnants of the universe's first stars. While massive galaxies like the Milky Way churn through generations of stars in a frenzy of collisions and supernova, these faint, ancient dwarfs have remained relatively untouched for billions of years. Their slow, quiet evolution and lack of heavy elements make them perfect cosmic time capsules, preserving conditions similar to the early universe. If population 3 stars still exist anywhere, these forgotten corners of the cosmos might be their last refuge. Think of these dwarf galaxies as the secluded villages of the universe, places where time moves differently and traditions remain unchanged. Unlike bustling galactic cities, where stars are constantly born and die in cycles of creation and destruction, these dwarfs have avoided the chaos. Their low metal content is the critical clue. Population 3 stars made purely of hydrogen and helium couldn't form in today's metal-polluted environments. But in these pristine dwarfs, where later generations of stars never seeded the gas with heavier elements, the conditions might still be right for a few ancient survivors to linger. The search is already yielding tantalizing hints. Astronomers have spotted stars in galaxies like Segway 1 and Ursa Major Roman 2 with such low metal content they're practically prehistoric. These stars aren't first generation themselves, but their unusual chemistry suggests they formed from the unaltered debris of population 3 supernova. It's like finding a recipe written in the handwriting of a long-dead chef. The ingredients are so pure they point directly back to the original source. Now, researchers are combing through these dwarfs with even finer tools, looking for stars so chemically simple they could only be relics from the cosmic dawn. But why would population 3 stars last longer in these environments? The answer lies in the dwarfs' gentle pace of life. Without the violent collisions and dense gas clouds of larger galaxies, stars in these quiet backwaters experience fewer gravitational disruptions. A first-generation star that formed slightly smaller, just tens of times the mass of our Sun, might have survived here, burning slowly in the cosmic equivalent of a low-stress retirement. Meanwhile, its massive siblings in busier galaxies would have long since exploded, their remains recycled into new stars. The hunt is far from easy. These dwarf galaxies are incredibly faint, often outshone by a single foreground star in our own Milky Way. Detecting individual stars within them requires painstaking observations with the world's most powerful telescopes, yet the payoff could redefine our understanding of stellar evolution. Finding even one true population 3 star in a dwarf galaxy would be like stumbling upon a living Neanderthal, a direct window into an era we've only ever reconstructed from fossils. And the implications stretch beyond just stellar archaeology. If these ancient stars are hiding in dwarfs, their light could reveal secrets about how the first galaxies formed. Did they grow from the inside out with massive stars at their cores, or did they assemble more chaotically with stars scattered like seeds in the wind? The answers could rewrite the story of cosmic dawn, showing us how darkness first gave way to light. So while the search continues, one thing is clear: the universe's oldest stories might not be written in the bright centers of galaxies, but in the faint, forgotten margins. And if we're patient and lucky, we might just catch a glimpse of the first light still shining against all odds. Detecting a population 3 star would be like spotting a firefly in a thunderstorm. The odds seem impossible, but the universe has a way of defying expectations. Think about how many breakthroughs in astronomy once seemed pure fantasy. A century ago, the idea of black holes was theoretical speculation. 50 years back, exoplanets were science fiction. Today, we photograph black holes and catalog thousands of alien worlds. The lesson: what's unimaginable in one era becomes routine in the next. The hunt for these ancient stars follows the same arc. Right now, it feels like searching for a whisper in a hurricane, but the tools we're building could turn that whisper into a shout. The biggest hurdle isn't just distance, it's time. Light from a surviving population 3 star would be stretched so thin by cosmic expansion that its signature might blend into the infrared haze of space. Current telescopes strain to pick up these signals, like straining to hear a single note in a symphony, but technology is evolving at a dizzying pace. The James Webb Space Telescope was designed to peer into these exact wavelengths. and upcoming observatories like the 30-meter telescope will push the boundaries even further. These instruments aren't just incremental upgrades, they're leaps into uncharted territory, with sensitivities that could reveal what's been hiding in plain sight. Then there's the role of sheer cosmic luck. Imagine a population 3 star passing in front of a distant quasar, its gravity bending the quasar's light in a telltale flicker. Such chance alignments, called microlensing events, have already revealed invisible objects like rogue planets and stellar remnants. A similar stroke of luck might unveil one of these ancient relics. Or consider the possibility of stumbling upon a star so metal-poor that its composition defies all known models, a celestial oddball that could only be a first-generation survivor. History shows that many landmark discoveries happen when scientists trip over something unexpected while searching for something else, but the real game-changer might lie in the data itself. Machine learning algorithms are sifting through mountains of astronomical observations, flagging anomalies human eyes might miss. These tools don't just look for what we know, they hunt for what we don't know, identifying patterns that don't fit existing categories. It's like having a cosmic detective that notices the one inconsistent detail in a vast crime scene. A population 3 star could be hiding in an old dataset, waiting for the right algorithm to expose its presence. And let's not forget the wild cards, those radical theories that could rewrite the search entirely. Maybe these stars aren't where we expect. Perhaps they've migrated to the outer fringes of galaxies, or dimmed into near invisibility by cloaking themselves in dust. Or maybe, as some models suggest, they've transformed into objects we wouldn't recognize as stars at all. The universe specializes in surprises, and the first generation of stars might be its greatest trick yet. So while the challenge is immense, so is the potential. Every technological leap, every unplanned discovery, every new way of interpreting data brings us closer to answering one of astronomy's oldest questions: how did the universe light up? The search for these stars isn't just about finding ancient objects, it's about testing the limits of our ingenuity. And if history's any guide, the cosmos loves proving that today's impossibilities are tomorrow's headlines. Finding one of these ancient stars would be like unearthing a perfectly preserved fossil from the dawn of time, except instead of bones, we'd be studying pure, unaltered stardust. Every atom in its core would be a relic from an era before planets, before galaxies, before even the basic chemistry of life existed. Imagine analyzing a star with no iron, no carbon, no oxygen, just the pristine hydrogen and helium that filled the universe after the Big Bang. Its light would carry chemical signatures untouched by later supernova, offering a snapshot of the cosmos in its simplest, rawest form. But the revelations wouldn't stop there. The star's size and temperature could rewrite our understanding of early stellar physics. Modern stars behave predictably based on their mass and composition, but population 3 stars operated under entirely different rules. Without heavier elements to help dissipate heat, their internal dynamics might have been wilder, their lifespans shorter or longer than models predict. A survivor could show us just how wrong or right our simulations have been all along. Even its rotation speed might hold clues, revealing how turbulent the gas clouds were when the first structures in the universe began to coalesce. Perhaps most thrilling is the possibility of discovering something entirely unexpected. What if these stars hosted exotic physics we've never observed? Magnetic fields stronger than anything in today's cosmos, bizarre nuclear reactions, or even traces of dark matter interactions frozen in their ancient light. The early universe was a laboratory of extremes, and a first-generation star would be its last remaining experiment, still running after billions of years. And then there's the bigger picture. By pinpointing where such a star lies, whether it's drifting alone in intergalactic space or nestled in an ancient dwarf galaxy, we could reconstruct the cosmic environment of the universe's first structures. Its position might reveal how matter clumped together in those early epochs, or how the first black holes began seeding the growth of galaxies. It's not just about the star itself, but about the lost world it represents, a world we've only ever glimpsed through mathematical equations and faint echoes in the cosmic microwave background. The hunt for these time capsules is more than a scientific challenge, it's a race against the clock. Every year that passes, the light from these potential survivors grows fainter, stretched further into invisibility by the universe's relentless expansion. But with each new telescope, each leap in computational power, we're closing in on the chance to touch a piece of cosmic history. And if we succeed, we won't just be observing the past. We'll be holding a conversation with it, one that began before time had meaning, and now just maybe we're finally ready to listen. Pondering the existence of those first stars isn't just a scientific exercise, it's a mirror held up to the deepest questions humans have ever asked. Who are we? Where did everything begin? And how does our fleeting moment in cosmic history connect to something as ancient as starlight itself? Every time an astronomer points a telescope at the edge of observable space, they're not just collecting data. They're tracing a lineage that stretches back to the very first flickers of light, a chain of events that led, improbably, to us. Think about the sheer scale of time we're grappling with. Those first stars ignited over 13 billion years ago. To put that in perspective, if the entire history of the universe were compressed into a single year, Earth wouldn't form until mid-September. Human civilization, the last few seconds of December 31st. Against that backdrop, the idea that we can study or even find objects from the cosmic dawn is staggering. It collapses time in a way that's almost spiritual. We're not just observers of the universe, we're its consciousness, a way for the cosmos to examine its own origins. And then there's the existential weight of what these stars represent. They were the universe's first alchemists, transforming simple hydrogen and helium into the elements that would one day build planets, oceans, and life. Without their fiery deaths, the periodic table would be barren. No carbon for DNA, no oxygen for water, no iron for blood. In a very real sense, we are their descendants, carrying pieces of those ancient giants inside us. That connection blurs the line between astronomy and genealogy. Searching for the first stars isn't just about completing a scientific model, it's about finding our cosmic ancestors. But the implications go deeper than chemistry. If some of those stars still burn, it would mean the universe preserves its history in ways we never imagined. We're used to thinking of time as linear, with the past irretrievably gone. Yet here's a possibility that defies that intuition, remnants of the beginning lingering into the present. It's like discovering a living parchment from the first page of a history book, one that's been quietly waiting to share its story. That idea alone reshapes how we think about existence. Maybe time isn't just a one-way street. Maybe the universe keeps its own archives hidden in plain sight. Ultimately, the search for these stars is about more than filling gaps in astrophysics. It's a quest to understand whether the universe forgets or remembers, whether the threads of causality that led to us are still visible if you know where to look. And whether, in the grand scheme of things, our own fleeting lives are part of something older and vaster than we can comprehend. Every photon we catch from the edge of time carries that question. Are we alone in the present, or are we in conversation with the past? The answer might be written in the light of stars that have burned since before time had meaning. The idea of ancient stars still shining today isn't just a scientific curiosity, It's a concept that's ignited imaginations for generations. From science fiction novels to blockbuster films, the notion of celestial relics from the dawn of time has woven itself into our collective storytelling. Think of the glowing, mythic stars in fantasy epics, or the alien civilizations in sci-fi that worship these cosmic elders as gods. There's something profoundly captivating about the idea that the universe's first light might still be out there, watching over the cosmos like silent sentinels. But where does the science end and the myth-making begin? One popular misconception is that these stars would look like the brilliant beacons we see in our night sky. In reality, a surviving population 3 star would be faint and cold, its light stretched and dimmed by billions of years of cosmic expansion. It wouldn't blaze like a Hollywood supernova, it might barely glow at all, more like an ember than a flame. Another myth suggests these stars would be easy to spot if they existed, but the truth is far messier. They could be hiding in plain sight, camouflaged among younger stars, or drifting unseen in the voids between galaxies. The universe is a master of disguise, and finding these relics is less about spotting a glaring anomaly and more about detecting the subtlest of whispers in a cosmic cacophony. Then there's the enduring legend that these stars hold the key to immortality or alien technology. While it's fun to imagine ancient civilizations orbiting them or harnessing their power, the reality is far less sensational. If we ever found one, it wouldn't be a gateway to lost knowledge. It would be a scientific goldmine, offering raw data about the early universe, but that doesn't make it any less thrilling. The real magic lies in what these stars could teach us about how everything began, not in fantastical tales of cosmic secrets. The line between fact and fiction blurs even further when you consider how these stars have been portrayed in culture. Some myths depict them as omens, their light carrying prophecies or warnings. Others imagine them as remnants of a lost creator's handiwork, divine artifacts in a secular cosmos. These stories reveal something deeper, a human desire to connect with the universe's origins, to find meaning in the vastness. Science, in its own way, is chasing the same goal. The difference is that astronomers aren't searching for symbolism. They're piecing together a puzzle written in physics and light. Yet the myths persist because they speak to something fundamental in us. The thought that we might share the cosmos with objects older than time itself is humbling, almost mystical. It's no wonder these stars appear in so many stories. They represent the unknown, the eternal, the untouched, and in that sense, the scientific quest to find them isn't so different from the ancient urge to reach for the heavens. Both are driven by wonder, by the need to understand our place in something unimaginably vast. So while we separate fact from fiction, there's beauty in the overlap. The myths remind us why this search matters, not just for the data it might yield, but for the way it stirs our curiosity. Whether these stars are still shining or long gone, they've already done something remarkable. They've made us look up and dream. And in a universe full of mysteries, that might be the most human thing of all. Solving the mystery of the first stars isn't a solo mission. It's a symphony of global collaboration, where astronomers, physicists, and engineers each play a crucial part. Picture observatories scattered across continents, from the high deserts of Chile to the frozen plains of Antarctica, all trained on the same patch of sky. Supercomputers in Tokyo crunch data collected by telescopes in Hawaii, while theorists in Berlin refine models based on observations from space-based instruments. This isn't just teamwork, it's a collective push to piece together a puzzle that spans billions of years, where every discipline brings a unique lens to the challenge. What makes this collaboration so powerful is the diversity of perspectives. Astronomers might spot a faint anomaly in a distant galaxy, but it takes physicists to interpret whether that flicker could be the signature of an ancient star. Engineers, meanwhile, design the next generation of sensors capable of detecting light stretched thin by cosmic expansion. No single team holds all the answers, but together they're closing in on the truth. Projects like the Sloan Digital Sky Survey or the upcoming Vera-C Rubin Observatory are testaments to this shared effort, pooling resources and expertise to map the cosmos in unprecedented detail. The data itself is a mosaic of contributions. When a telescope in New Mexico captures a curious spectrum, it's uploaded to international databases where researchers from Sao Paulo to Seoul can analyze it. Open access archives and real-time alerts mean a breakthrough in one lab can spark a eureka, a moment halfway around the world. This transparency accelerates discovery, turning what might have been decades of isolated work into a dynamic, global conversation. It's like assembling a jigsaw puzzle where every scientist holds a different piece, and only by fitting them together does the bigger picture emerge. But collaboration isn't just about sharing data, it's about challenging assumptions. A theorist's model might predict that surviving population 3 stars should glow a specific shade of infrared, while an observer's data contradicts it. These tensions aren't setbacks, they're opportunities. They force teams to revisit ideas, refine instruments, and sometimes rewrite the rules entirely. The debate over dark stars, for instance, grew hotter when particle physicists joined the conversation, suggesting exotic dark matter interactions that astronomers hadn't considered. It's this friction between disciplines that often sparks the brightest ideas. The human element is just as vital. Behind every algorithm and telescope are scientists who have dedicated careers to this quest. Some grew up marveling at the night sky in rural villages. Others studied in bustling metropolises. Their shared passion bridges languages and cultures, turning competition into camaraderie. When the James Webb Space Telescope beams back its first images of the early universe, it's not just a win for NASA or the ESA, it's a triumph for every researcher who's ever wondered how the first light pierced the darkness. And the stakes couldn't be higher. If one team's hunch leads to a confirmed sighting, it wouldn't just validate their work, it would reshape our understanding of cosmic history. The discovery would ripple across textbooks, inspire new technologies, and maybe even answer existential questions about our place in the universe. But until then, the search remains a testament to what humanity can achieve when curiosity transcends borders. In a world often divided, the hunt for these ancient stars reminds us of a simple truth. The universe's greatest mysteries are too vast for any one nation, any one mind to solve alone. Chasing the universe's oldest light isn't just a technical challenge. It's a philosophical journey that forces us to confront profound questions about our place in cosmic history. Every time we train a telescope on the edge of observable space, we're not just collecting data, we're grappling with the ethics of exploration itself. What does it mean to uncover secrets from a time before time? And how do we honor the stories these ancient stars tell without imposing our own narratives onto them? This search blurs the line between discovery and interpretation, reminding us that science is never just about facts, it's about the meaning we assign to them. Take the concept of firstness itself. Labeling something as the universe's inaugural star carries weight, implying a linear narrative where the cosmos unfolded in tidy chapters. But what if the truth is messier? Simulations suggest star formation in the early universe might have been chaotic, with multiple generations overlapping in ways we don't yet understand. By fixating on finding the first, we risk oversimplifying a complex dawn, much like early astronomers who insisted the Earth was the center of the solar system. Our frameworks shape what we see and sometimes what we miss. Then there's the responsibility that comes with discovery. If we found a surviving population 3-star, its light would belong not just to humanity, but to the universe itself, a relic from an era when our planet didn't even exist. Unlike archaeological treasures tied to human cultures, these celestial artifacts transcend ownership. No single nation or generation can claim them, raising ethical questions about how we share such knowledge. Should access to these observations be unrestricted, or do we need protocols to prevent commercial exploitation or weaponization of cosmic insights? The answers aren't in any astronomy textbook. This search also holds up a mirror to our biases. For centuries, Western science prioritized observation over indigenous cosmologies that often wove celestial phenomena into intricate spiritual tapestries. Today, as we decode the physics of the first stars, there's growing recognition that multiple ways of knowing can coexist. Some indigenous traditions, for instance, describe stars as ancestors or teachers, a perspective that, while not scientific in the traditional sense, enriches our emotional connection to the cosmos. Bridging these worldviews doesn't mean abandoning rigor. It means acknowledging that wonder and curiosity take many forms, and what if the hunt fails? The pressure to deliver breakthroughs can tempt researchers to overinterpret ambiguous data or prematurely declare success. History is littered with examples, from the Martian Canal's illusion to the faster-than-light neutrino fiasco. In our eagerness to find the universe's first light, we must resist the urge to see patterns in noise. This isn't just about academic integrity, it's about respecting the mystery. Some truths might remain forever beyond our grasp, and that's okay. The cosmos owes us nothing. Yet for all these complexities, the pursuit matters precisely because it humbles us. Staring into the abyss of deep time puts human conflicts and achievements into perspective. The same starlight that once ignited the cosmos now fuels our imagination, linking the quantum flickers of the Big Bang to the neural flickers in a curious mind. That's the paradox of this quest. While we search for ancient stars, we're really searching for ourselves, trying to understand how stardust became sentient and what that means for whatever comes next. Future missions now in development could revolutionize our hunt for the universe's first light. While today's telescopes push the boundaries of detection, projects like LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, and HAB-X, the Habitable Exoplanet Imaging Mission, are engineering marvels designed to see farther and clearer than anything before them. Imagine optics so precise they could spot a candle flame on Pluto, then amplify that sensitivity 1,000-fold. That's the level of detail these observatories promise, turning what's now theoretical into something tangible. LUVOIR, with its staggering 15-meter segmented mirror, would dwarf even the James Webb Space Telescope's capabilities. Its design isn't just about size, it's about spectral range. By capturing ultraviolet through infrared light with unmatched resolution, it could isolate the faint infrared glow of a population 3-star from the cosmic background noise. Think of it as tuning a radio to a frequency no one else can hear, picking up whispers from the cosmic dawn that current instruments miss entirely. HAB-X, meanwhile, takes a different approach. Its starlight-blocking coronagraph would cancel out the glare of younger stars, revealing dim, ancient objects hiding in their shadows like shy ghosts at a crowded party. But spotting these relics isn't just about raw power, it's about strategy. These missions would target specific cosmic neighborhoods where simulations suggest first-generation survivors might linger. The outer fringes of galaxy clusters, the diffuse halos around ancient dwarfs, even the voids between superclusters, all become hunting grounds. Advanced algorithms would then sift through petabytes of data, flagging anomalies in starlight that hint at pristine hydrogen-helium compositions. It's a cosmic needle in a haystack search, but with tools fine-tuned for the task. The implications of success would ripple across astronomy. Confirming a population 3 stars' existence wouldn't just settle a decades-old debate, it would validate entire branches of cosmological models. Does their light match predictions about the early universe's density? Do their lifespans align with theories about dark matter's role? Each observation would refine our understanding of how structure emerged from primordial chaos. And if they're absent where models say they should be, that disruption could be just as revealing, forcing us to rethink star formation's fundamental rules. Yet these missions represent more than scientific milestones, they're testaments to human curiosity. Building them requires international collaboration, billions in funding, and engineering so audacious it borders on alchemy. The fact that we're willing to invest so much in chasing cosmic ghosts speaks to something profound, our need to connect with the universe's origin story. Whether Louvois or HAB-X finds a first star or comes up empty, their data will illuminate corners of cosmic history we've only dreamed of exploring. The hunt isn't just about answers, it's about learning which questions we haven't even thought to ask yet. You might think finding the universe's oldest stars requires billion-dollar telescopes and teams of PhDs, but some of the most exciting discoveries in astronomy start in backyards. Amateur astronomers, armed with nothing more than passion and patience, have a long history of spotting cosmic oddities that professionals miss. From comets to supernova, hobbyists have repeatedly proven that keen eyes and dedication can uncover secrets hiding in plain sight. And now the hunt for population 3 stars could be the next frontier where everyday stargazers make history. The key lies in the sheer volume of the night sky. Even with automated surveys and AI, professional observatories can't monitor every star continuously. That's where distributed networks of amateur astronomers come in. By tracking unusual object stars with odd color shifts, erratic brightness, or unexpected chemical signatures in their spectra, citizen scientists can flag anomalies for deeper study. It's like having thousands of additional eyes scanning the cosmos, each one a potential lifeline to a discovery that might otherwise slip through the cracks. Projects like the American Association of Variable Star Observers have already shown the power of crowdsourcing. Volunteers regularly contribute data on pulsating stars, eclipsing binaries, and other celestial variables, creating datasets far richer than any single institution could compile. Now, initiatives are adapting this model to search for metal-poor stars in our galactic neighborhood. Using affordable spectrographs attached to backyard telescopes, amateurs can analyze starlight for the telltale absence of heavy elements, a possible smoking gun for a surviving first-generation star. But why would a population 3 star turn up so close? The Milky Way's halo, a sparse outer region of ancient stars, is prime real estate for cosmic relics. Over billions of years, gravitational interactions could have flung these stars from their birthplaces into the galactic suburbs, where they might now drift unnoticed. Unlike distant targets that require massive observatories, a nearby relic could be bright enough for amateur equipment to detect if someone knows what to look for. The beauty of this approach is its unpredictability. Professionals target specific regions based on models, but amateurs often stumble onto wonders by accident. Take the case of Boyajian star, whose bizarre dimming pattern, first spotted by a citizen science project, sparked years of debate about alien megastructures before settling on a dust-based explanation. A similar accidental discovery could happen with a population 3 star, turning an amateur's routine observation into a scientific landmark. Technology is leveling the playing field like never before. Affordable high-resolution spectrographs, once the domain of universities, now let hobbyists dissect starlight with precision. Online platforms like Zooniverse aggregate amateur observations into searchable databases, while apps guide users to uncharted stellar anomalies. Even smartphone cameras, when paired with the right filters and processing software, can contribute meaningful data. The tools are there. It's just a matter of time before someone points them at the right patch of sky. And the impact wouldn't stop at a single discovery. Confirming that amateurs can spot these relics would democratize the search, unleashing a global army of observers. Schools, astronomy clubs, and even curious individuals could join the hunt, transforming abstract astrophysics into a hands-on adventure. Imagine a high school student in Norway or a retired engineer in Chile becoming the first to identify light from the cosmic dawn, proof that wonder isn't confined to research institutions. This isn't just about adding another star to the catalogue. It's about redefining who gets to participate in humanity's oldest question: where did we come from? Every time an amateur astronomer peers through an eyepiece or adjusts a spectrograph, they're not just stargazing, they're time-traveling, sifting through the universe's deepest memories for clues to our origins. And in that search, even the smallest backyard telescope can become a window to the dawn of everything. Gravitational waves, ripples in the fabric of space-time, might hold the key to unlocking the secrets of the first stars without relying on their fading light. Unlike photons, which get stretched and dimmed as they cross cosmic distances, these waves travel undisturbed, carrying pristine information from the universe's most violent early moments. Imagine trying to reconstruct a thunderstorm by studying only the lightning. You'd miss the thunder's deep rumble, a whole dimension of the event. Gravitational waves are that thunder, offering a complementary way to hear the cosmos when its light is too faint to see. The idea hinges on the cataclysmic deaths of those ancient stellar giants. When massive population 3 stars reached the end of their lives, many likely collapsed into black holes or exploded as supernova, sending shockwaves through spacetime itself. These disturbances would have propagated outward at the speed of light, surviving billions of years to potentially reach our detectors today. Current observatories like LIGO and Virgo aren't yet sensitive enough to pick up signals from such distant events, but next-generation instruments like the Einstein telescope or space-based LISA could change that. Their advanced sensitivity might catch whispers of collisions or explosions from the cosmic dawn, like eavesdropping on a conversation from the edge of time. But gravitational waves aren't the only indirect window into this elusive era. Another promising avenue lies in the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light might encode shadows of the first star's influence. As their ultraviolet radiation ionized the surrounding hydrogen, it created bubbles of charged particles that subtly altered how the CMB's photons traveled. By mapping these distortions with telescopes like the Simons Observatory or future CMB S4 projects, astronomers could reverse engineer the distribution and timing of those early stellar births, like deducing the shape of a long-vanished fire from the scorch marks it left behind. Then there's the ghostly glow of infrared background light. Even if individual population 3 stars are invisible, their collective output might linger as a diffuse haze across the sky. Missions like SphereX are designed to scan for this faint signal, which could reveal the total energy output of the universe's first stellar generation. It's like measuring the warmth of a room long after the candles have burned out. The heat remains, hinting at the flames that once flickered there. Perhaps the most speculative but thrilling method involves quantum entanglement. Some theorists propose that primordial quantum fluctuations, stretched by the universe's expansion, might have left imprints on the spins of certain particles. If detectable, these cosmic bell tests could indirectly probe conditions from the first star's era. While this remains hypothetical, it underscores the creative lengths scientists will go to bypass the limitations of traditional astronomy. Each of these techniques shares a common thread. They turn the universe's other phenomena, space-time ripples, background radiation, even quantum weirdness, into tools for indirect detection. The first stars may never reveal themselves directly, but their echoes could be hiding in plain sight, waiting for the right technology to tease them out. And when that happens, it won't just be a triumph of engineering, it'll be a masterclass in cosmic ingenuity, proving that sometimes the universe's oldest secrets are written in more than just light. For all our cutting-edge telescopes and supercomputer simulations, the universe's first stars remain stubbornly out of reach, not because they're impossible to find, but because the cosmos plays by rules we're still deciphering. Consider this: even our most powerful observatories can only capture a fraction of the light that's traveled billions of years to reach us. The farthest objects we've detected, like the galaxy GNZ 11, are glimpsed as they were over 13 billion years ago, yet their light shows signs of heavy elements, proof they're already second-generation systems. The true pioneers, those pristine population 3 stars, lie just beyond the edge of our vision, their light stretched into near invisibility by cosmic expansion. It's like standing at the shore of an ocean, knowing there are islands beyond the horizon but lacking the tools to sail there. This isn't just a technical limitation, it's a fundamental barrier woven into the fabric of space-time itself. The universe's expansion creates an observable horizon beyond which light hasn't had time to reach us, placing the earliest epochs permanently out of view. Even if a first-generation star still burns today, its light may be redshifted so severely that it blends into the cosmic microwave background, lost in the static of creation itself. Our models suggest these stars should exist, but the universe offers no guarantees that our equations match its deepest realities. After all, nature has a habit of defying human expectations, from quantum entanglement to dark energy. What's humbling is how much we're forced to infer from indirect evidence. The chemical fingerprints in ancient quasars, the subtle unevenness in the cosmic microwave background, the odd metal poor stars in our galactic backyard, these are all secondary clues, like reconstructing a dinosaur from scattered bones. We know the first stars must have existed because we see their aftermath, but their true nature remains as elusive as a shadow in fog. Even our most advanced simulations rely on assumptions about conditions we've never observed, from the density fluctuations in primordial gas to the behavior of dark matter in the early universe. Small errors in these assumptions could lead us wildly astray, like navigating by a slightly miscalibrated compass. Yet this uncertainty isn't failure, it's the engine of discovery. Every unanswered question about the first stars represents a frontier where new physics might lurk. Could dark matter interactions have altered their life cycles in ways we haven't imagined? Might quantum gravity effects, negligible in today's cosmos, have played a role in their formation? The gaps in our knowledge aren't blank spaces so much as doorways, inviting us to question deeper and look harder. When the James Webb Space Telescope failed to find as many pristine early galaxies as predicted, it didn't mean our models were wrong. It meant the universe had surprises in store, pushing us to refine our understanding of how structure emerges from chaos. There's profound beauty in this unfinished search. Astronomy, perhaps more than any other science, teaches us that mystery isn't the opposite of knowledge, it's its necessary companion. The same cosmic darkness that hides the first stars also guards their secrets with a kind of generosity, ensuring we'll always have new questions to chase. After all, a universe that revealed everything at once would leave no room for wonder, no incentive to build better telescopes or dream bolder theories. The fact that we can ponder these distant giants at all, using starlight and mathematics to bridge billions of years, is its own kind of miracle, and who knows? The question of whether the first stars still exist isn't just about ticking a box in an astronomy textbook. It's about tracing our cosmic ancestry. These ancient giants weren't just the first sources of light. They were the architects of the universe as we know it, forging the elements that would one day become planets, oceans, and even us. The search for them is more than a scientific challenge. It's a journey to the very beginning of everything, a quest to understand how darkness first gave way to light. Consider what's at stake. If we discovered a population 3 stars still burning today, it wouldn't just confirm a theory, it would rewrite our understanding of stellar lifetimes, dark matter's role in the early cosmos, and the conditions that allowed galaxies to form. Every flicker of light from such a star would carry imprints of a universe before chemistry, before complexity, before time itself had settled into the rhythms we recognize. On the other hand, if we never find one, that absence would be just as revealing. It might mean the first stars were even more extreme than we thought, burning too fiercely to leave survivors, or that our models of the early universe need a radical overhaul. But here's the beautiful paradox of this search. Even without definitive proof, the hunt has already transformed astronomy. The tools we've built to scan the cosmos for these relics, like the James Webb Space Telescope's infrared eyes or supercomputer simulations of primordial gas clouds, have unlocked discoveries far beyond their original purpose. In trying to glimpse the first stars, we've uncovered ancient galaxies hiding in plain sight, mapped the cosmic web with unprecedented clarity, and even refined our measurements of the universe's expansion. Sometimes the questions we ask matter more than the answers we find, because they push us to see further and dig deeper than we ever thought possible. And that's what makes this more than just a scientific endeavor. It's a testament to human curiosity, to our refusal to accept that any mystery is beyond reach. For millennia, we've looked up at the night sky and wondered where it all began. Now, armed with technology and imagination, we're closer than ever to touching that origin story. Whether the first stars still shine or vanished eons ago, their legacy is written in the atoms of our bodies, the light of distant galaxies, and the endless questions that keep us searching. So the next time you gaze at the stars, remember, you're not just seeing points of light, you're looking at chapters in a story that began with the first flickers of nuclear fusion in the cosmic dark. And somewhere out there, in the vast expanse between galaxies or hidden in the glow of an ancient dwarf star, the universe might still be keeping one of its oldest secrets. The hunt isn't over, it's just beginning.